All right, let's take some notes on what a force is. A force is just a push or a pull on an object, and this causes an object to change its state of motion. There are two kinds of forces, two categories of forces. They are contact forces and non-contact forces. Let's go over contact forces. Contact forces are forces that exist when objects touch. The first type of contact force is known as the support force, also known as the normal force. And you can denote this by F sub support or F sub normal. The support force is exerted by an object when it is in contact with another object, and this can occur in any direction depending on how the two objects are in contact. Many people tend to have a misconception that support forces are always in the opposite direction of gravity, and so support force is always going up. And in this case, with the book on the table, the support force is going up, which is in opposition of the force of the weight here that the book is experiencing. But if an object is on a ramp, for example, your support force is going to be at a perpendicular angle to that of the surface that the object is resting. Tension is another force that is transferred through a string, rope, cable, or wire. It is a force that pulls. That pulling force acts from opposite ends. So if you're looking at this hand here, this person is holding a mass by a rope. Notice that the tension is being felt in two directions on both ends of that rope. Here we have a person on a tightrope in the center, and you see that the tension is being pulled in both directions. So this is what I mean when I'm saying that the pulling forces act from opposite ends. Spring force, F sub spring, it is an elastic, compressed, or stretched force. This is experienced when we have a spring that is either being stretched or pushed down. So if you were to stretch it and let it go, it would have energy, and that force would pull that spring back towards the surface. If you were to push down on that same spring, it would push away from the surface. Here you have a rubber band. If you were to pull it, then you would experience that spring force. Air resistance, also known as drag, and here we will have it denoted as F sub air, is the resistance of an object that is moving through the atmosphere. So, for example, if you had a parachute, you would experience air resistance going upwards while gravity is attracting you downwards. Even though you're running and it might not feel like it, you do experience some air resistance. And so in this case, you are pushing yourself forward while experiencing air resistance in the opposite direction. Again, also here with the vehicle, and we're experiencing thrust and air resistance in its opposite direction. Applied force is any push or pull on an object. For example, if you were pushing a table, or pulling a table. The direction that the force is being applied is the direction of that vector. If you were to kick a ball, then what you're showing is the applied force is in the direction of your kick. Thrust is an applied force, and it incorporates mechanical means. So anything that has an engine is going to give thrust. For example, here we have an airplane that is using fuel in order to propel that plane forward. Now, upthrust is an applied force to an object that is floating in either a liquid or a gas. And we can see that with hot air balloons, where the upthrust would be going upwards. And of course, here on a boat in the water, we would also have upthrust. Friction force is a major force that is experienced when any two bodies are in contact. It is when one body slides over the other, or it is where the bodies cling together despite any external forces. It is a resistive force. When you have friction, it creates waste heat, and this is directed parallel to the object surface, and it does depend on the material, the texture, and the load. So these three factors determine whether or not an object will experience more or less friction. So for example, with loads, Here we have a rubber material that is on a road surface, and the road surface is the same in both cases, but the difference is the amount of rubber that you have, or how much mass and pressure is being exerted on this rubber, will determine how much contact is being made between the material and the road surface. The more contact between the two surfaces, the higher level of friction. Of course, it does depend on the material. For example, if you had rubber versus another object like glass or plastic. And then with texture, if something is more smooth, it will have a lower level of friction, versus if it was more rough, then it would have a higher level of friction. Every surface has irregularities. They are jagged, peaks and troughs and dips. And these, when two objects collide and they scrape over each other, they give rise to a force that resists the motion. Depending on how many troughs and peaks there are, will dictate whether or not they have a high level of friction. And what causes this is electrostatic attraction between the atoms of the contact, which make it crash into each other and not allowing another object to slide over it. There are two kinds of friction, static and kinetic. With static friction, it is when there is no relative motion between the bodies. So if you are pushing a block and it does not move, this is static friction. That force that keeps the things from starting to move, that is what static friction is. So here you see a block that is being applied with some force to the right. And in the opposite direction, because this box is in contact with the surface that it is sliding on, it is experiencing static friction. And this is denoted as F sub S, or you can spell it out static. Notice that this is in opposition to the applied force. We also do have the force of gravity acting on the box, and in its opposition, the support force, also known as the normal force or the force of reaction. Because all the arrows, all the vectors are equal, we have a net force of 0. The box is not moving. To make the object move, you have to overcome the force of static friction. And so you have to continue to push this box or pull this box. You must apply some force that will then eventually overcome the amount of static friction that this object is experiencing. Imagine pushing a block. This is just an example. If you're pushing a block, it doesn't move, then you know that the friction must be equal but opposite to the pushing force. So here is where you have static equilibrium. You have the friction matching the applied force. As you push harder, the object is still not moving. The friction force grows with the pushing force. So as you continue to push, the friction will match the push until the block just starts to move. Once the block begins to move, the friction force goes down considerably. This is now called kinetic friction. Now the friction that is in the opposite direction of the applied force is called a different name. So if the same force is applied that was used to start the block moving, the block will now begin to accelerate. Here is a graph that shows the amount of force applied in relation to the amount of friction that is experienced. So here it starts with 0. As you increase the amount of applied force in newtons, the amount of friction also increases until it reaches a point where the object begins to move. What you'll notice is at this threshold of motion, then mu will not be static anymore. It will change to a value which is mu sub k, or mu sub d for dynamic. And notice here that it drops, and then you're able to accelerate or just keep a constant velocity for your object that you're moving. But it does take a certain amount of force in order to push it past the threshold at which the object will begin to move. So let's take notes on kinetic friction, also known as dynamic friction. It is when two surfaces move past each other, and it is when you are pushing on the object and it is moving. Remember that when the object is in motion, that friction is weaker than static friction. Here we have our box with the applied force to the right, and the kinetic friction is much smaller than the applied force. Because the vector is greater in the direction of the applied force, the net force is to the right. Acceleration is also to the right. So we've covered all of the major contact forces. Let's talk about non-contact forces. These are forces that exist without any contact between objects, and one kind of non-contact force is gravitational force. This is due to gravity, and gravitational forces are long-range attractive forces that are between all objects that have mass. So anything that has mass is matter, and all matter has gravitational force. So for example, here we have an apple that is falling to the ground. Even though the earth is not in contact with the apple, it is pulling, it is attracting the apple to the Earth's core. Electrical or electrostatic forces is another non-contact force. This is essentially the attraction and repulsion of charges. So when you're thinking of electrons and protons and how they behave, when you have a proton next to an electron, those are attracting each other, versus if you have two protons or two electrons, they will repel each other. And here you see an example of the Van de Graaff generator where we have repulsion of charges. We also have magnetic forces. It is a pushing or pulling force on objects that have iron. For example, we have metal pins that are being attracted to a magnet here. When discussing forces, we need to talk about something that is called restoring forces. And this is any force that causes an object to return to its original size and shape, which is its lowest point of energy or its equilibrium point. So for example, we have a ruler, and when a ruler is in its normal state of stillness, we know that its rest state is right here, perpendicular to the surface of the ground if it is held up straight. If you were to pull the ruler in either direction and let it go, that force which pulls it back to its center is known as its restoring force. You can also see that with the spring. If you have a spring and its resting state is right here, where its net force is 0, if you were to compress the spring, it would go back and forth between its equilibrium point until eventually that state would be achieved again. All right, we've made it to the end. Hopefully everything makes sense, and we're going to practice this in class next. Have a wonderful day.